Today I want to show an alternative to STLinks, which is just using the virtual COM port via USB. What is a virtual COM port? It's basically the debug which you're familiar from, for example, Arduino projects, where you can just write to the microcontroller. That is the idea, but without extra hardware, just with the STM32. I have as a project, oh wait, here you can see the points. It's no extra hardware. You can debug, control, and flash STM32s. Basically any microcontroller, but with STM32s I did it. And I have here an ESC I'm currently working on. And for your concern, it's just an STM32 with an USB port and no STLink, just USB port. And just to see what you can do with it, here I have the Arduino IDE. It's not as strong as a custom console, but you can go with basic commands. Like I have here with a question mark, you can see like infos, and it is very rudimentary right now, but for example, you could use this command to just hear a frequency of the ESC. Doesn't matter, you can build your custom commands, but that is the idea. So you can basically talk to your STM32. For the flashing and debugging, you need a custom console, which I have built as well, but that is too much for this video. Yeah, so how does it work? Basically, you need to enable the virtual COM port, and then you need to enable talk with and talk back to the COM port in an easy and portable way. To do this, you need to install and start Cube MX with a project with your microcontroller, or you need the normal STM32 ID. Both will work, whatever you prefer. And you need to enable everything that your USB port needs. That depends on which STM32 you're using. In my case, I think I need the high-speed clock, but I'm not sure I'm enabling it anyway. Also, you need USB. So here it's already activated. You see it at the pins. And also you need here an USB device and an virtual COM port. That is basically the serial connection to your computer. And you don't need DFU, device firmware update. We will come to that later. But we are just using the virtual COM port and implementing the device firmware update by custom code, which is actually not that hard to do. So in the project manager, you need where you want to create your project. I think you're familiar with STM32 already, but basically you can say, okay, I want a CMake project, or I want a project for the Cube IDE, and then you can compile it whatever you like it. I'm using CMake, so let's use CMake, and then you generate code. I'm not going to use that example, but that's the basic setup. Yes. So now you need any kind of IDE where you can start implementing the feature we want. And let's look in more detail. We want to send commands, and I really love the printf format from C, so I want to implement this. So to do this, you need a few more settings. You need to go in the CMake list. There's more stuff in there that you won't need. It's a bigger project. But the important thing is that you here need to copy this command. It enabled floating points, and yeah, this one as well. They all make sense. They will make it a bit slower, but then you have the normal printf with floats. Yes. So there is a simple command. I can go in here. There's this command which sends just stuff to the over the virtual COM port to whatever is connected to it. And this command is used for the printf. I think you know it already. But basically you have those huge function which takes a format string, which is formatted in the printf style, and then those command just make sure that it's right orientated and formatted. So it basically converts this format string to bytes which can send out via CDC transmit. It's a complex function, but basically it works. If you can use it then here with debug f and then hello world and maybe a variable. 20. Okay, when I compile this, then that's you can just choose whatever port, doesn't matter. Here you can see we received that data as well. Yeah, but that's just the first step in this video. Let's talk about receiving data on the STM32 here, receive commands. And basically what there's one method that's important for this. It's this one. And this method basically handles a buffer. And here you can see it's in the USBD CDC if function folder thingy here. Here's the path. And basically it handles one buffer, and this buffer is always getting the data which gets received by the COM port. And then you could say, okay, let's just make here some method which handles the receiving data and executes a command, for example, or reads ADC or whatever. But the problem is that's not really portable, because everybody who's wanna use that will need to change this method somewhere in its file structure, and it's really annoying. And you can't also override this method. You can just comment it out, but that's the same as changing it. So that's really ugly. So I found a nice workaround to just look at the buffer, and every time it gets changed, I take those data and write a 0 in the first thing of the buffer, the first element. And as long as there's a 0, I do nothing, because there's old data. And if new data comes in, I take the data out and then put a 0 again back there. So that's non-intrusive. And the only thing I really need is a buffer. And that buffer is here, the RX buffer. So I just import here the header from that driver, basically. That is important, you need this. And then I just access the buffer via the extern keyword. So I use the buffer from that header and from that driver. And then I have this nice method which is called console check, and this one is the main driver for receiving commands. So how does it work? At first, here is a small logic which just checks, is it the first time that this command is running? And if it's running for the first time, then there's nothing received yet, because everything is new. It's a new start. So I set the first element of the buffer to 0, and also I use this keyword to disable this logic. So yeah, this variable will keep its value even between function calls. So if that's 1, this one won't get called, and it won't do this all the time. Yeah, so the first buffer is 0, and there's new data coming in. So the moment new data is coming in, basically I want to call this one as often as I can. I just run it in the main loop. Here you can see it. It is always running, and there should be not a lot of delay, so it's working tight and quickly. And so every time new data comes in, that buffer gets changed. There is no 0 anymore because there's new data. New data always starts at the start in this configuration. So this one detects if there's no 0 anymore and then handles the incoming data. And after the handlement, it sets the first element to 0 to reset the whole system. So yeah, and here is basically a rough structure, so I can send commands and parameters down the line. What do I mean by that? It's a simple structure, it's not the ideal structure, but it's very easy to implement and very easy to troubleshoot. And the basic idea is I wanna be able, oh no, it's the wrong firmware. I wanna be able to send a string command, which is maximum 4 chars long, and I want to send 4 parameters, so I can change anything I want to do. I'm gonna refresh the console and be right back with the right software. Okay, so now I have the console again on my STM32 board, so I can send. For me, I always program question mark, so I can look up which console with things I programmed in. You can see here it received the question mark, and also those 4 ones are empty. And then it's a bit of a mess, but you can see the point. Like if I use a program, the PA changes frequency and duty cycle of something. So let's say I want to have 1 kilohertz and 0.9 duty cycle. Here you go, 1 kilohertz, 0.9 duty cycle, and I can change that as whatever I want to have as a comment. Now I show you how. So basically it receives the string and the 4, in my case it's floats. I want to have string and 4 floats, but you can program it whatever you like. And then it prints that again, so I know it got received. Here you can see received, blah blah blah. And then that's basically just a fancy switch case. It makes an integer of the 4 chars, so I can use it efficiently and quickly. And here, for example, it's just a question mark command, and then it prints some helping and stuff. And here B, for example, is like the battery voltage. We can try this again also. Here it prints the battery voltage. There's no battery connected, but it doesn't matter, like you get the point. Let's talk about firmware updates. There is an open source tool which is called DFU. I can open it quick. Here. Basically what it does, it allows you to flash your microcontroller with a binary file. So if I hold down the boot pin, you need to look for yourself where the boot pin is on the STM32, and then connect power. Then you do not run the normal code. You run in a device firmware update configuration. And then if you use this tool, I'll show you how. I downloaded it before, and I have it here in a folder. Do I find this folder? So here, I have a few files, but the most important files are DFU util, or if you don't want to use all the other files and you want to use it as a standalone, you can use a static version. I'm gonna try this one, but it's basically the same if it's in this folder. And if you just run the file with /l, with -l, then you get an overview which DFU devices are connected. And in this case, there are 4 devices connected, and it's the different files storage which this controller offers. So it offers the internal flash, but there's also memory, optional bytes, and device feature doesn't really matter. The only thing we are concerned is the internal flash, because that one we want to change. We want to get our software on the internal flash. So how do you do this? You need to go on the CMake and use here, you need the binary file, because normally CMake just does some internal files which are not useful with DFU util. So you need to convert here the output file to a binary file. For this you need that command. Just add it and it's gonna add a binary file. Okay, so if you got this, you see if you build your project, you will get here a binary file in debug and build debug, and then you can use that binary to flash the microcontroller. Let's do this. So basically you need this command, and it's quite long, and I'm gonna not explain a lot of it, but basically what it does, here you have the where you want to load your program, and you can see here it's the same. It's not the same number. No, it's the same. Here I want to write to the internal flash, and this one is just optimization and random stuff. And I want to call it util.exe, and with the /d you define where your binary is. Okay, I found the command. Here you can see it. You can just copy paste it. This one is the address where you wanna get your firmware to. So please select the internal flash. It's the only thing that makes sense for the most users. And then /d, and then you need where your binary is. So in my case, to get back up one folder, and then I want to go to the build folder, and then to the debug, and then there's esc, that's just my name, .bin. It is the path you set here, so whatever set here you should use. And then it is not running. Windows needs this. Yeah, and then here you can see it found the device, and then it erased the previously installed firmware and uploaded the new binary, which of course works. I'm gonna see in a minute. Yes, so yeah, here that is my startup screen, so it did reboot quite nicely if I replug it in. But this is the peasant way to use this. I do not wanna unplug it, press the boot button and plug it in again every time I wanna flash my ESP. So the last thing we're gonna do right now is here the firmware updates over this console. So right now we just use an external tool, but I want to go in that DFU mode without the use of unplugging it, power cycling it, and use the boot pin. That's annoying. So that is the real strength, because theoretically you won't even need a boot pin for your ESP for this to work. You just need to short it once, and then it's gonna work. So we have an extra command here. In this command, if I find it, here it is. This command is dfu, and what it does, it calls a function jump to dfu bootloader, and this function just sets the bootloader via code. So it stops the virtual COM port from happening, and then disables all interrupts. And you should put everything like ADC, timers, you should disable all that stuff. I'm not using it on this project, so it doesn't matter for me, but like everything you have enabled, you should disable here. And then here you jump basically the internal point vector, which says where the STM32 is in its internal memory, that jumps to the bootloader. and then with a reset and reload you are in the DFU. And let's show you this. If I send the command DFU update and it's not connected anymore because the virtual COM port is closed. And if I now use this, you see it's available as DFU upload, and we can upload it again. So yeah, that was my short introduction in how you can use the virtual COM port as a debugger on STM32. If you have any recommendations or questions, please put it in the comments down below, and goodbye.